Hello, I am Onjun and this is our project of Digital Electronic System course. Our assignment is called ALU Design of ISCV CPUs. I have 3 members in this group. First is Jingye, second is Chen En, and third is me, Zhenjie. And our lecturer is Dr. Ismail Ali. Let's start to the introduction parts. Let's go to the introduction parts. First, RISC-V is an open and free processors architecture that allows anyone to design custom processors. And these openness allow companies with resources and even students like me also can build our custom processors without registrations. I think it's a flexible and efficient processors architecture designed to execute simple and optimized basic instruction like floating point calculations, better processing and security enhancement, and so on. And I think its design is simple and powerful, making us making it efficient for everything from tiny smart device like handphone or like CPU to high performance computer like graphic card or like AI like this. And we come to the ALU Alimentix logic circuit. I think he's a core part of our processors. He will handle like the Alimentix and logical operations like mathematical functions like addition, subtraction, multiplication, and division as well. As he will use like AND gate, OR gate, and SOR gates. Apart from that, he will also interact with the register like flip flop, like the D flip flop we know, which are small and fast storage locations for input operations and result within the CPU. And together, when the RISC-V and ALU work together, they will create an efficient and flexible computing system, and then enable the adaptable, cost-effective, and powerful processors for device applications from smart device to AI system. And next, we come to the block diagram and gas schematic of ALU design. Like this one is the multiplexers A and B, and this one is adder and subtractor, and this is the flip-flop part. Okay, we have 8 inputs, which is A0, A1, A2, A3, B0, B1, B2, B3. Total 8 bits, and B7 and A7 are 2 bits each for the multiplexers, and ALU OP is the carrying inputs for the adder and subtractor, and we also have clock and reset for 1 bit each. Okay, when we come to adder and subtractor, the operation of adder and the operation of the addition and the subtractor is dependent on the ALU OP. When ALU OP is equal to 1, so it will do the additions. When ALU OP is 0, it will do the subtraction, A minus B. Okay, and this is a functional table of the 4 multiple ones multiplexers. Okay, you can see the output is Y, so I/O is also is equal to A0 or B0, when S1 is equal to 0 and S0 is equal to 0. And this is the Boolean expression of the outputs. And this one is the block diagram of the multiplexer. A1, A0, A1, A2, A3, and S1, S0, and the Y output is in here. Okay, and this is the gate level schematic diagram of 4 multiply 1 multiplexer. You see, there's A0, A1, A2, A3 inputs. Also, AS1 and AS1 and ASO also is the inputs. And here is the AND gates, and here is the OR gates. And we'll output only 1 bit of Y only. Okay, and this is the 4 multiply 1 multiplexers. So you will see there are 4 multiplexers here. Okay, so every input have 4 bits each, and we'll insert to their certain positions, and we'll output 4 bits outputs. Okay, when we come to the and this is the gate level of schematic, you see have A, B, sinks, carry, and sum. And this is the Boolean operation of the sum, and this is the Boolean operation of the carry, and this is the logic circuit of full adder. You can see there is SOR gate and the AND gate and OR gates. Okay, when we come to the adder and subtractor, it means that adder and subtractor is a 2-in-1 function. Okay, and here when the ALU OP is 1, so it will adder like the additions, and the ALU OP is equal to 0, so it will function as like subtractor. Okay, and the next part, and this is the register for the D flip flop parts, and this is the 4 bit D flip flop parts, which the input will come from the output of the adder and subtractor, and this is clock and this is reset. Okay. When we come to the ALU Alimentix logic, it means that you see this is a multiplexer for the A parts. You can see this the input is A1, A0, A1, A2, A3, and this is the multiplexer for the B parts, B0, B1, B2, B3, and this is the adder and subtractor. The A and the B parts will adder together, do the addition or the subtraction depends on the ALU OP, and the output will connect to the register will become the input of the register, and function it will output the results ALU outputs. Okay, and this is the waveform result of the 1 bit 4 multiply 1 multiplexers. As you can see, the color of friend is red, so I just when the AS1 is equal to 0, okay, this one is equal to 0, and ASO also equal to 0, okay, also equal to 0. It will take the A0, it will take the A0 parts, and A0 is shown is equal to 0, so the Y will become 0. So you can see this is the multiplexer functions, and next is 4 bits multiplexers. It's also same design, but include 4 bits in once. Okay, like we also see for the A cells, S1 and ASO will pass together become A cell. Like 0, 0 pass together will become 0, 0, 1, 0, 1 plus 0 plus 1 will become 0, 1. So it always depends on the A cells. Like A cell is 0, 0, so he will pick the A0, and with the red flags, like here is 0, 0, and it will pick A0. So it's 1, 0, 0, 1. So A out will equal to 1, 0, 0, 1. It's just like that. Okay. When we come to the full adder parts. Full adder parts like this one, it has 3 inputs, AI, BI, and C ins. And we also have 2 outputs, sum and carry. So it was like that. when the A is 0, B is 0, and the C is 1. So only 1 at the additions. So it means that only 1 is the sign is 1 and the carry will become 0. So you see sign is 1 and carry is 0. So it's right. It's like this one is a waveform result of 4-bit added substrator. Okay. You can see this ALUOP when 1s will become additions, but it will enter the NOR gates and become zeros. Okay, we will do this first, and we see the A inks. Okay, when the A is 111, we see here 111, and B inks is 1010. B ink will enter the SOR gate, which he will do the SOR operations like this one, and SOR operation will also include the ALUOP after the NOR gates. The result will become sense 1010 with the ALUOP is 0. Okay, and the B ink after the SOR operations will pass with the A inks and pass with the ALUOP after the NOR gates. It becomes 1001. So this is the addition pass. And we come to the next, which is the subtraction pass. Like ALUOP is 0. After he enter the NOR gates, he will become 1. And A ink is 1001, and the B ink is 001. Sorry. Okay. Because the ALUOP after the NOR gate is 1, so it will influence here SOR operation. It will become invert the bits of the B inks. So you see when the B ink before enter the SOR gate is 0101, but after the SOR gate is become 1010. Okay, so when the Y output is equal to ALUOP after enter the NOR gates plus A inks and plus B ink after the SOR gate, 1 plus 1001 plus 1010 equal to 0100, and this is the subtraction. Like you can see here, which is equivalent to A ink minus B ink. 101 minus 0101 equal to 0100. Okay. Okay, we come to the next part, which is a D flip-flop part. This is a waveform of the D flip-flop with the resistors, and it have 3 inputs and 1 outputs. The most important input is resets. When reset is equal to 0, no matter if CLK is equal to 0, 1, or the positive edge, or Y is 0 or 1, output will definitely become 0, which is clear. Okay. When the RS is equal to 1, so it will depend on the CLK and Y inks. Okay. D flip-flops is a positive edge. It will occur when the positive edge is exists, like this one, when the arrow is to the ups. So Y is equal to 0, and the output will be set to the 0. And when the CL clock is arrow to the ups, and Y equal to 1, so the output will be set to the 1. And this is the what's the principle of the flip-flop. And come to the ALU parts. Like ALU parts, as we can see, this is the table of the ALU. Like this is a possible value for the ALUs, and this is the derived parts. Like okay, for example, like we take the this one, the first one. Like okay, we see the A cell first. Like A cell is 10. 10 is meaning that you want to take the A2 inks parts. So it will take 0101, which I highlight, the parts I highlight. Okay, when it comes to the B parts, like the B cell is 10, so it's also take the B2 inks. So 0101, 001, 0101 and 0010 will do the additions due to the operations, and it will it absolutely will come as is the 0111, and our result is also sent, so compile is sent. Okay, and we finally come to the discussion part. When we come to the discussion part, we know that K-man will key in or optimizing the circuit design by reducing the number of logic gate and simplify Boolean expression using a graphical approach, eliminating the redundant turns and streamlining components like the full adder, substrator, and the 1-bit 4 multiply 1 multiplexer. And these simplifications reduce the gate counts, making the circuit more smaller, more faster, and more efficient. Fewer gates mean lower power use, shorter delays, and improve the performance, which enhance the ALU responsiveness in real-world applications. And when it comes to the conclusions, K-man help us to minimize the logic gate counts and simplify the Boolean expression, resulting in a more efficient and high-performing ALU design. This method demonstrates the value of systematic optimization in digital circuit. And the next part is our reference, and the next part is the rubric of our projects. And that's all from our presentation. Thank you for your patient listening.